In this video, we're actually reviewing once more the common denominator method of evaluating a limit. The reason why this method is actually a common denominator case is because anything to the power of a negative 1 is actually going to take this entire entity, so this 9, and it's going to flip it into a fraction. Now, the reason why I'm not going to say that it's moving it to the denominator is because if I take this entire thing to the power of negative 1, then this entire thing is going to flip into a fraction, meaning it's going to move the entire thing into the denominator. But because each of these pieces separately have a power of negative 1, each of those pieces separately become the denominator of a new fraction. So, this 9 to the negative 1 becomes 1 over 9. This 9 plus x to the negative 1 becomes 1 over 9 plus x, and x is still in the denominator. Notice again, this is very similar to the last example we looked at, such that I can rewrite this as x approaches 0 of 1 over x, knowing that if I try to plug in 0, I'm going to be dividing by 0 here, I'll be dividing by 0 here, I'll be dividing by 0 here. Notice algebraically I'm not removing that so-called problem child yet. But by moving it off to the side gives me the ability to look at it like this, such that I can see that I need to find a common denominator between these two terms. And again, I'm not touching that because that term right there, that x in the denominator, has to cancel out for me to be able to plug in x equals 0. So, I'm now going to go ahead and find a common denominator between these two pieces. That common denominator is 9 and 9 plus x, meaning that this limit becomes the limit as x goes to 0 of 1 over x times the common denominator of 9 plus x, and on top, if I were to multiply this piece here by 9 plus x, it'll become 9 plus x, minus, if I multiply this entire piece, so on top and on bottom, by 9, I'm left with 9. And now I'll see that 9 minus 9 with an x left over. So I get the limit as x goes to 0 of 1 over x of x over 9 plus x. Now I'm going to make a point to state here that notice how every single time I'm doing some algebraic manipulation inside of the limit, but I do not remove the limit operator. That function doesn't disappear. That limit operator will remain there until I've actually evaluated the limit. When do we evaluate the limit? We evaluate the limit when we can physically plug in the value for x. So again, notice I'm rewriting the limit as x goes to 0 because in this case I did not plug in 0 yet. But now that I'm plugging in 0 for x, and my limit ends up becoming something that is evaluatable, providing me with a singular, simple number, I can simply remove the limit. So again, by plugging in 0 here, this next step, you'll notice the limit is now gone. Now, if you were asking about how we would write this final result, it simply is the entire original limit is equal to 1 over 81. We make sure that the function is part of that limit. It's not the limit equals, it's the limit as x approaches 0 of this entire function equals 1 over 81. So you will never simply write the limit as x goes to 0 is equal to. This is poor notation. Every limit as x goes to something should have some kind of function in the interior of that limit, and that's going to go to some value.